Now that we've seen the N-type and P-type transistors, let's put them together into different logic gates. We're going to start with an inverter, which is also known as a NOT gate. A NOT gate has two transistors, a P-type on the top, which is connected to the supply voltage, and an N-type on the bottom, which is connected to ground. And the input is connected to both gates, to both the P-type and the N-type gate. Now there's a connection between two of the terminals on the P-type and the N-type transistors, and the output is connected to that point. Now a truth table for an inverter is very simple. We have two possible values of our input, 0 and 1, and the output is just the inversion of that. When I have an input of 0, I have an output of 1, and vice versa. Let's look at how these P-type and N-type switches work when I have the different inputs. So first let's look at an input of 0. With an input of 0, that closes the P-type switch. Remember, with an P-type device, if I have a gate input of 0, that closes the switch. So we're making a connection here for the output up to the supply voltage. But with an N-type device, when I have an input of 0 on the gate, that opens the switch. So I've broken the connection to ground to 0 volts. So here the output is going to be pulled up to the supply voltage. So the output will be connected to the supply voltage. And that looks like a logic 1. Now when we have an input of 1, the opposite occurs. The P-type switch opens and the N-type switch closes. That breaks the connection to the supply voltage, but makes a connection to ground to 0 volts. So the output is connected to 0 volts, or a logic 0. Now let's talk about a little bit more complicated gate, and that's a NOR gate. A NOR gate you can think of as an OR, and we've already understand an OR. When any of the inputs is a 1, the output is a 1 also, followed by a NOT. So that's going to be just the opposite. Whenever I have an input of a 1 with a NOR gate, then the output is 0. And when I have all zeros, the output is a 1. A NOR gate has 4 transistors for a 2-input NOR gate. So we have our 2 inputs, A and B, and with a NOR gate we have 2 P-type devices connected in series up to the supply voltage. And we have 2 N-type devices in parallel connected to ground. So what this means is that in order to get C, the output, pulled up to the supply voltage, I have to have both of the P-type switches closed to make that connection. However, on the bottom, I can have either of the N-type connections, N-type devices, switches closed in order for C to be pulled down to ground. Let's look at an example now where I have an input A equals 0 and B equals 1. So here with A equals 0, the top P switch is closed, but with B equals 1, the bottom P switch is open. So there's no connection now to the supply voltage. With B equals 1, one of those N-type switches is closed, so I make a connection now of C down to ground, so C becomes a logic 0. So here's the truth table for a NOR. And again, it's an OR with the output inverted. So I have my 2 inputs, A and B. Here are 4 possible values. And only when A and B are both 0 do I get an output of 1. Otherwise, I get an output of 0. A NAND gate you can think of as an AND followed by a NOT. Here the structure is different than a NOR. Here the 2 P-type devices on the top are in parallel, which is the opposite of a NOR. And at the bottom, the N-type devices are in series. So for the top, so long as either A or B is 0, I'm going to make a connection to the supply voltage, and C will be pulled up to a logic 1. At the bottom, I have to have both A and B to be 1 to close both of those N-type switches so that C becomes a 0. Here's an example where I have A equals 0 and B equals 1. With A equals 0, then one of those P-type switches is closed, so I make a connection of C to the supply voltage, so C becomes a 1. However, with A equals 0, that also breaks the connection at the bottom. That opens up the corresponding N-type switch so that I have no connection. So here you see that property that we talked about with these type of CMOS devices, where I have either a connection to the supply voltage or a connection to ground, but never having both. Here's a truth table for a NAND. with my 4 possible values of A and B and my output C. So again, you can see that this is like an AND followed by a NOT. So only when all of the inputs, in this case my 2 inputs A and B are 1, do I get a 0, and otherwise I get a 1.